Hokie dokie. It's pretty much 4 o'clock, so we are going to get started. But just before we get started, I want to announce, if you are watching this and have not seen, that I'll be doing a reading day raffle. Feel free to check out this video. This video is for members only, which you are a member if you are watching this. So click on this video, and to enter the raffle, you just have to comment on that video. It's basically just like a members only raffle, but you know, I want people to comment so they know they're a part of the raffle instead of just including everyone who's a member into the raffle. So if you haven't, commented on that and want a chance to win a bunch of fun gift cards, go ahead and comment on that video. All right. Today we're doing basically the last live session for any quiz this semester. Pretty crazy. Come a long way. It's been a good run this semester. Doing these live sessions, that is. Next live session will be for the final for this class, and it'll probably be available to everyone. So this is probably the last exclusive thing I'm doing for the weekly study session peeps. So let's get into it. Quiz 10. To give you a little background on Quiz 10, Quiz 10 in this course used to be quizzes 11, 12, and 14. So what I'm saying is your Quiz 10 has 3 quizzes worth of material on it in one quiz. So that's why it's a lot. And it's related stuff. It's a lot of stats and probability stuff. So I guess I see why they put it all together. There actually used to be a 5th exam, which basically was Quiz 10 material. So with that in mind, I just have like a little bit of each quiz. I probably have still 20, 25 questions total here. But just to give you a taste of what Quiz 10 is, I definitely recommend studying a little bit more than just watching this video. So keep that in mind. I'm going to go to this live session just in case someone happens to be watching and they have any questions. Let me default that. All right, so we're going to 2-minute late start here. Sorry. Let's get started. Number 1, starting with a standard American deck of 52 cards, you created a smaller collection only containing cards with a dime. Okay, so using the smaller deck, what is the probability of drawing a queen? So it's important to understand how a deck of cards works. Goodness, my pen's not working. That's good. It's important to understand how a deck of cards is organized. 4 suits, spades, clubs, hearts, and diamonds. So we have just created a deck with the diamond suit, and each suit has 13 cards. So basically, if we just have a smaller deck with diamonds, that means we have 13 cards in this smaller deck, and we are wondering what the odds are of drawing a queen. So there's only 1 queen out of those 13 diamonds, and so 1 out of 13 is what we're looking for here. So this question, it's a lot of that kind of probability stuff with the deck of cards. I think I have one more with the deck of cards. Let's see what they got. Suppose a royal card, a jack, queen, or a king is drawn. Then, after replacing the first card, a second card is drawn. What's the probability that the second card is also a royal card? Now, it's important to note whether they replace the first card or do not, because I think sometimes they do replace it, other times they do not. If they draw a card and then replace it, meaning they put it back in the deck, there are still 52 cards in the deck once they've put it back. If they draw a card and they do not replace it, then there are now 51 cards in the deck. So it changes your probability for the second card to something over 51 typically. So if we have replaced we've replaced the first card, so there are 52 total cards still. They ask what's the probability that the second card is a royal card. So we still know we're drawing from 52 total. And they ask what are the odds of drawing a royal card? Well, there's 3 royal cards per suit, and there are 4 suits. So 3 times 4 is 12. So we'd be looking for 12 over 52, or if that simplifies, dividing each of these by 4 gives us 3 over 13. So I think we're looking for that. That's it. All right. So that's a little taste of those. I would definitely recommend going back over a bunch of examples for those, as well as these ones here. They say, assuming the probability of having a boy or a girl is the same, what's the probability that a family with 3 children has at least 2 girls? So what we want to think about are basically all the combinations, or all the, combinations, all the organizations or something that a family could have with 3 children. So what I mean is, like, what are all the outcomes if you have 3 children? So we're going to start with the outcome that all their children are boys, and then we're going to go to the outcomes where you have 2 boys and 1 girl. There should be 3 of these, because the 2 boys could be together, they could be on either end, or they could be together over here. Or you could think about it as the girl is on the right, the girl is in the middle, the girl is on the left. However you want to organize it. I'm a very visual person, so kind of noticing where the girl is probably a little more helpful. So this is all boys. These are the 2 boys, 1 girl. And then let's keep going. We do the 2 girls, 1 boy. So girl, girl, boy. I'm going to put the boys here first. Then do the girls. So 3 options for 2 girls, 1 boy. And then the last option is, if they have just all girls. So in total what we have is 1, 2, 3, 4, 5, 6, 7, and 8 possible total outcomes. They ask, what's the probability that they have at least 2 girls? So we're basically gathering all the possibilities where we have at least 2 girls. So that means 2 or more girls in these outcomes. 2 girls, those options, I guess, start in this category here, where we have 2 girls, 1 boy. And then 3 girls is the last option. So having at least 2 girls takes up 4 out of these total 8 outcomes. So 4 out of 8 is equivalent to 1 over 2. So we're looking for 1/2. Hope that makes sense. There's scenarios for this problem where they ask about a family with 3 children, and then another scenario where they ask about a family with 4 children. So in that scenario, instead of 8 outcomes, there should be 16 total outcomes. So take a look at those, try to practice those, get good at those and what they're asking for, all that jazz. But there's a little glimpse into that problem. A certain blood test accurately indicates the presence of a disease 98% of the time when it's actually present. A test indicates the presence of a disease 0.4% of the time when the disease is not present. If 3% of the population has the disease, what percentage of the total population will receive a false positive? A lot going on here. I like to sort of organize it in like a tree diagram. So let's jump right into that. I like to break it up into the percent of the population that actually has the disease versus not having the disease. So if 3% have the disease, I'm going to put D for disease, and then ND for no disease. So 3% totally have the disease, right? Which means 97% totally do not have the disease. They tell us that a certain blood test indicates the presence of the disease 94% of the time when it's actually present. So 94% of the time, it will accurately indicate that the disease is there. So 94% of those 3% will find out that they have the disease accurately. But what that means is, of the 3% that actually have the disease, 6% of them will not find out. They'll be told that they do not have the disease, even though they do. In other words, a false negative. Yeah. Why 6%? Well, if 94% are going to be accurately, true, then 6% are going to be falsely false. Not accurately false. I don't know. I'm bad with the language, but I hope that makes sense. And then the test indicates the presence of the disease 0.4% of the time when the disease is not present. So when the disease is not present, 0.4%, they'll indicate the presence of the disease. Okay, in that case, let me put that over here. because I'll do like left is like presence of the disease. So I'll say like disease, and then like no disease, or like the test indicates no disease. So disease, test indicates no disease, something like that. Might be a little confusing, I'm sorry. So 0.4% will be told that they have the disease, even if they do not have the disease, okay? Which means of the 97% people that do not have the disease, the 99.6% of them will be accurately told that they do not have the disease. That's pretty solid, okay? So now they ask what percentage of the total population will receive a false positive. So I probably didn't need to make all these tree diagrams for just this one question, but I figured I'd lay it out for every scenario you could think of. So let me actually just follow through with that. This would be like a true positive. This would be a false negative. This would be a false positive. This would be a true negative. Okay, so I'm looking for false positive, right? False positive would be, I think, just this kind of string here, this branch. So false positive means that they do not have the disease, but they will be told that they do have the disease. So really all we do is take 97% and multiply it by 0.4%. Now what that looks like, well, actually, let's not worry about what that looks like as a decimal, because our answer is in percentages. So 97 times 0.4.
It's 38.8.
All right, I got 38.8. Did I do that right? 97 times 0.4? Seems a little fishy. Did I do something wrong? Hope not. Leaning towards the one that I got. I feel like I'm missing something. 3% has the disease. False positive. Give me a sec here. 0.97 times 0.004. Does that work? For some reason that worked when I wrote it like that. Okay. Alright, for some reason, that's strange. I thought it would have worked out. Okay, I don't know. For some reason my phone's being funny, but it worked when I wrote it as decimal. So I'll just tell you to do it as a decimal. So what I mean is I wrote this percentage as that decimal and this percentage as that decimal. So 0.97 times 0.004. 0.97 times 0.004. And we get 0.00388, which does translate to 0.388% as a percentage. So I think we're still, we're looking for D. Okay. Hope that makes sense more or less. Spent a little more time on that than I would have liked, but hope that makes sense. That's a little insight on that problem. I have a bunch of examples worked out for those. Feel free to check those out. Let's keep it pushing. Got a lot to go through. Number 5, considering human blood types. If a parent with genotype AO and a parent with genotype AO have a child, what's the probability that the child has phenotype O? So the idea here is to make what's known as a Punnett square. So you just put, one parent and another parent on top and the side there, and we write out the intersections. So AO, AA, AO, AO, and OO. And they're asking what's the probability that the child has phenotype O. So to have phenotype O, you want to use this chart, which comes straight from the Math MPO sort of textbook. So we're looking for phenotype O. The only one with type O is this genotype, double O. So even if there's O's in it, but there's A's and B's, those will be type A and B respectively. You need to have double O for type O. So when we look at our Punnett square, which one of these is the double O, or do we have any double O's? And we do. It's just one of those 4. So one of those 4 is double O, which means only 1 in 4 chances of having a child with phenotype O. Okay, that was 5. Let's do number 6. Another example here, real quick. AA and BB are the parents' genotypes. So we make our square, we find the intersections, all ABs, and they ask what is the probability that child has phenotype AB. AB is all 4. 4 out of 4 is equivalent to 100%. They will have a child with phenotype AB. So you'll notice AB is its own phenotype. It's not just like an A or a B, like one of the type A's or type B's, but it's its own phenotype. So to be AB, it has to have A and B. So just, be comfortable knowing these phenotypes and genotypes, and you'll be fine on that one. It's not too bad. That was number 6. Let's do number 7. Sort of a step up from the last one. I remember there were like years that I had no idea how to go about this problem, and I actually just had to watch one of my videos to relearn it. But like right before I made the video for this, like a year ago, I had just learned it, and I was super stoked to finally know how to do it, because for years I just didn't know what I was doing. All right, so if you have a parent with genotype AAQQ and another with AAQQ, what's the probability that you have phenotype trait 2? So the first thing we're going to do with the first parent, we think about what are all the combinations you could have just with this parent of A's and Q's. So all the combinations we could have would be capital A, capital Q. You could have capital A, lowercase q. You could have lowercase a, capital Q. You could have lowercase a, lowercase q. Those are all the combinations of A's and Q's amongst the first parent's A's and Q's, okay? And then second parent, we have A, little a, capital Q. What are all the combinations there? We have capital A, capital Q, or lowercase a, capital Q. And that's it. That's all the combinations we have of A's and Q's. So what we do now is make a Punnett, I guess, rectangle. I don't know if it's still considered a Punnett square or not, but we make the rectangle thing with these parent 1 and parent 2's combos there. And then we do the combos of all the intersections. So 2 capital A's, 2 capital Q's, 2 capital A's, alternating Q's, alternating A's, capital Q's, and so on. You get the idea. A lot of focus here, sorry. Give me a minute. A, Q, Q. All right, good enough. So now they ask, what's the probability that the child has phenotype trait 2? So what helps me is first identifying what are all the trait 2s. What are we looking for? So the first one we have is, let me use a highlighter. Be a little better. So we have alternating A's and Q's, which we see here, here. I think that's it. And then we got lowercase a's, alternating q's. Got that here. I think that's it. And then all lowercase. Do we got all lowercase? We do not. So how many do we have highlighted? We have 3 highlighted out of the total 8 possibilities in the Punnett chart, square, rectangle, whatever. And so 3 out of 8 are the odds that the child has phenotype trait 2. Okay, that's pretty much it. That's the whole thing. So definitely practice those. Those can be a little weird. But I have a video with like 6 examples though, so feel free to check that out if you need more help. That was number 7. Let's do number 8. Oh shoot, you know what? I got one more. Look at that. So again, do parent 1's combos of A's and Q's. So we just have a capital A, capital Q, capital A, lowercase q. And then here we have lowercase a, capital Q, lowercase a, lowercase q. So here we just have a cute little square. Just, not to scale, but it's supposed to be a square. And let's find the combos. Capital A, lowercase a, capital Q's, capital A, lowercase q, capital Q, lowercase q. alternating again. And then A, Q, Q. Might have done that backwards. I don't know how they do it. No, we got it right. Okay, so then what's the probability that the child has trait 2? So we'll go through trait 2 again. So capital A, lowercase a, Q, Q. We got that here. And that's it. And then trait 2, got lowercase a is alternating Q's, no lowercase a's, which means all these are goners. So then we just have 1 out of the 4. So we're looking for 1 and 4 for this one. Okay. Not too shabby. That was number 8. Let's keep going. Number 9. You are working as a student researcher in a lab. PI gives you some data and you interpret it. That's a very confusing, it's a crazy context. Basically just look at this data here and they're asking about how it's correlated. So if the correlation was approximately 0, that means that you would just have like completely random scattered points. There would be no kind of pattern to it, or like positive or negative slope. It kind of everything would just be scattered everywhere. And then negative versus positive correlation are kind of similar to like negative and positive slope. And so in this case, this one has a negative slope. In other words, a negative correlation. The way you would describe it is like as x increases, the y values decrease. Therefore, that is a negative correlation. Okay, that was number 9. Here's number 10. They say estimate the correlation coefficient, otherwise known as the R value. The R value ranges from -1 to +1, and if it's closer to 1 or -1, the correlation is stronger than if it is closer to 0. So that makes sense. So closer to -1 or +1 means a more like definite positive or negative slope. The closer it is to 0, the more it looks like a scatter plot like this. So that's why C is our answer here. So the next example we see, you'll see why. You can probably see the answer there for a second. That was number 10, so this is 11. So they say, what's the correlation coefficient for this one? You can kind of see that positive behavior, so we know it's not negative. And we could probably say it's not 0 because it's not completely randomly scattered, but you can see that bubble filled in for C. It's 0.65 because it's positive, but the points aren't, tight enough together to be 0.9. So that's kind of what you want for 0.9. You want them to just be a little bit closer to the main line that's like passing through. You don't want to see them spread out as much. Okay, so that's a little insight there. That was what, 11. Let's do number 12. We're going to do this with the help of Excel here. Let's break out Excel. Shoot, not Spotify. Ooga booga. All right. In the data set below, what percentage of the variation in y is due to a linear relationship with x? This is another way of asking for what's known as the R-squared value. R-squared is literally the R correlation coefficient we just talked about squared. So we are going to find that by doing, we're just going to type in this data first. So exactly how we see it, 10.2, 13.8, 20.3, and so on. A little slow right now. Give me a minute. That wasn't right. Hopefully that's all right. And I think to find this, you can just use equals correl, correlation coefficient. Oh, that's one way of doing it. So what this will do is give you the R value, and then you could just square that. And then I'll show you one more way to find it. So for this one, you have to highlight one array, array 1 and array 2, right? So you highlight the X values first, make sure to put a comma, and then highlight the Y values. put the parentheses, and then hit enter. So again, this is just the r value, and we're finding the r squared value. So we're literally going to square this. And we get 0.723. And as a percentage, that is 72.31. Okay, let's talk about one more quick way to find that. So you highlight this data, you can actually insert a scatter plot. Beautiful. With this scatter plot, go to add chart element, trend line, more options, and make sure to go to the options here with the bar graph looking thing. And if you go to display r squared, it'll just straight up give you the r squared value like that. So a couple of different ways to go about it. Hope that helped. Let's get back to it. That was number 12. Let's do number 13. There it is. All right. Which of the following is true for the population data below? Mean, mode, range. Okay. Well, a lot of this you could do by hand. A lot of it you could do in Excel. I would say go ahead and just do most of it in Excel. I don't think I picked the greatest question for this problem here, but that's all right. We're going to input the data and talk a little bit about how to use Excel. So 7.6, 10.4, 7.6, 7.6, 36.3, 10.4. Oh boy. All right. This thing on. Check, check. All right. Just making sure. So I think I got all those right. Oh, man. All right. 10.4, 7.6. All right. Second, let's talk a little bit median, mode, range. I think most of these are just functions in Excel. So let's start with median. Median. Look at that. Returns the median. So let's finish that. Highlight these, hit enter, we get 10.4. So they say the median is 10.4, so that checks out. How about the mode of the data? I think mode's a function, maybe. Mode single, mode multi. Let's just go mode single. 10.4, look at that. Mode is also 10.4, I'll take it. And we could also see that, I guess, because 10.4 shows up the most. It shows up like 3 times, as well as the median. If you are unaware what median stands for, median is the like middle of the data. So if you listed all of these in order, numerical order, then the middle of these 10 data values would be the median. Now the range is just the max minus the min. I'm not sure if there's a range function. Nope. But you can do maybe like, if you are really lazy, you could do like max of this, which would find the maximum value minus the min value of that. And we get 40.3. Or you could just find the highest value, which is 47.1, and subtract the lowest value, which is that the highest value? No, I feel dumb. Hold up. Let me make sure. No, 47.6 or 47.1. And then, yeah, subtract the lowest value. Oh, 6.8. That's why. So subtract the lowest value of 6.8, and you should get 40.3. Yeah. Anyway, so all of these are correct. Now, I don't know if I have another one that's better than that. Yeah. A thing to mention about this specific problem. Sometimes they ask for things like standard deviation and maybe the mean, and that's pretty much it. Let's talk about a couple different things though. So like to find the mean, you can just use the average function. So average of all this. So the mean would be 20.63. Sometimes they ask for the standard deviation of the population, for which you would use stdev.p. So this is the standard deviation of the population. Once you highlight those and enter that, sometimes that's for the standard deviation of the sample. So pay close attention to what they're asking for to find different standard deviations. I think that's pretty much all they ask for. Sometimes they might say like the modes are, or like this is bimodal or something. So bimodal just means like there are multiple most often occurring data points. So like if 10.4 occurs 3 times, but let's say there was another data point that also occurred 3 times, then that would be bimodal, and like those would be your 2 modes, I guess. So that's all I'll say on that one. That was number 13. Let's keep going to number 14. Let's drink a little Crystal Light raspberry lemonade. That's solid. That's real solid. All right. They tell us the mean survival time is 15 years with a standard deviation of 2. Based on a treatment, the predicted survival time is 2.5 standard deviations beyond the mean. How much longer is the patient expected to survive? Okay, this is a matter of z-score, basically. So z-score is equal to x minus the mean. I'll just write it out like this. X minus mean over standard deviation, where x is like the data point, I guess. So x is actually what we're solving for here. The mean is given to us, and standard deviation is given to us, which means that z is the number of standard deviations from the mean. If it's a positive z-score, say positive 2, that means we are 2 standard deviations beyond the mean, like after the mean, to the right of the mean. If they said -1 standard deviations, that means you are 1 standard deviation behind or less than the mean. Okay, so because they say 2.5 beyond the mean, we know that z is a positive 2.5. We're solving for x, and we're going to subtract the mean of 15. And then, I think I'm doing this like a way more complicated way than you need to. I'm going to follow through with this, I guess, but I'll just tell you how to do this a lot easier. Sorry. So it's the same process, just not as, algebraic. So we're going to solve for x. So we're going to multiply by 2. 2.5 times 2 is 5. We get x minus 15 equals 5. So we add the 15. And we get 20 equals x. So 20 is our answer here. So yeah, now that I remember, I think this one you can literally just do like the standard deviation times the number of standard deviations, because they tell you it's that many standard deviations past the mean, and then just add it on to the 15. So if you know you are 2.5 standard deviations beyond the mean, which is 15, and you know the standard deviation is 2, then you are 2 times 2.5 after or added on to 15. Does that make sense? Hope so. Let's keep going. Number 15. According to the empirical rule, what is the probability that z is between 0 and 3? Okay. Assume the data is normally distributed. So giving you a little bit of insight, z-scores and normal distributions, empirical rule, all that is related to this normal distribution curve, otherwise known as a bell curve. That's pretty much it, where the mean lies in the middle, and then you go 1, 2, 3, and just like barely over 3 standard deviations in either direction. So you go like plus or minus 3 both ways. And again, these are like your z-scores. So they're wondering what's the percentage of this curve that is between 0. So z-score of 0 means you're starting right at the mean in the middle. What percentage of this data is between 0 and 3? And you can see it's almost like half the curve, right? It's roughly 50%. So you could make an educated guess and say it's that 49 situation there. But I'll talk through how to find this in Excel real quick. So that's a little background, I guess, this image. But let's use Excel. So what are we going to do in Excel? Let's find out. we're going to use it to find the probability that z is less than or equal to 3, and then find the probability that z is less than or equal to 0, and then we're going to subtract them, and then that'll be it. So what we're getting is this. So we're going to do norm s dist. I think that's it. Yes, so norm s dist equals norm s dist is a function that allows you to input a z-score and get the percentage of the curve that is to the left of that z-score. So to explain that again, if I did norm s dist and plugged in a z-score of 0, and the cumulative part, so we plug in a z-score and a cumulative. Cumulative just means it adds up to 1, and it'll always be 1. So let me hold this here, sorry. If we plugged in a z-score of 0 and cumulative of 1, it means it would give us the percentage of this curve that is to the left of the z-score of 0, because we plugged in a 0 for the z-score. So if we plug in a z-score of 3, it's going to give us basically excuse me, the percentage of the curve that's to the left of a z-score of positive 3. So it's going to be almost 100%. But then we're going to plug in a z-score of 0, and it's going to give us all this. So then if we subtract this area from the entire area, then we're going to be left with what was in here. So I feel like I explained that kind of poorly, and I apologize, but basically whatever the high boundary is, just find that. Whatever the low boundary is, find that, and do it in Excel here. So let's actually demonstrate. 3, 1, again, cumulative is always 1, and then we're just going to do minus norm s dist for 0. So 0, 1. So what we've done here is basically input this in Excel like this. So this is what we're doing. Hit enter, and we get 49865. I'll just call it 4987. So if we convert that to a percentage, we're looking at 49.87, which is roughly 4985. Okay. Hope that was kind of helpful. I think I have one more here. That was number 15. Here's number 16. Here they say, what's the probability that z is greater than -2? So if we plug this into Excel, let's kind of demonstrate this. If I just were to straight up plug in -2, 1, this will give me the percentage of the curve that is to the left of this z-score. So what do I mean? I mean -2 is right here, roughly. And they're giving me the percentage to the left, or the percentage of the z-scores that are less than -2 or equal to -2. And they're saying this is equivalent, and my curve's not extremely to scale, but they're saying it's equivalent to roughly 2.275%. But they don't want to know the percentage to the left, they want to know the percentage to the right. And if we know this whole curve, the area under this whole curve makes up 100%, we are going to take 100 and subtract 2.275. So the easy way to do that is just start it off with this. If you know that z is going to be greater than that z-score there, you just do 1 minus this. 100% minus that. So 1 minus that gives you 97.7%. So we're looking for, well, that's lovely. They have 97.5 and 97. Whew. All right. Well, I'm gonna go with my gut here. Go with the higher one. Sorry, those two were very close. Yeah, just do the best you can on that. Put your trust in picking the one that's closest to what you find out. All right, that was number 16. Here's number 17. Let's get into it. They have a frequency distribution. While calculating the relative frequencies, he realized he forgot to record a piece of data. What is the relative frequency? Of the missing data for outcome E. The most helpful thing about all these outcomes and all these probabilities is that all these probabilities should add up to 1. In other words, 100%. So if you add up all of these, they should equal 1, which means, how do we find this empty space here? We just do, you could add all these up and then subtract it from 1, or you could just do 1 minus each of them. However you want to do it will get you the right answer. I'm going to do it in a fun way with Siri. 1 minus 0.09 minus 0.05 minus 0.42 minus 0.17.
The answer is 0.27.
All right, 0.27. That was a very cursed Siri voice. I don't think I chose that setting, but okay. 0.27 is our missing data point to make all those probabilities add up to 1. That's all I can say about that. It's not too hard, hopefully. Here's number 18, I think. Yep. All right, so this one might be more of like the z-score situation. They say the data is normally distributed with a mean of 130, standard deviation of 24. They say how many standard deviations from the mean would a dose of 59 be? So this is very much textbook z-score stuff. So they give us the mean of 130, standard deviation of 24, and the data point of 59. So again, it's like x minus the mean over the standard deviation equals z. So x is like the data point, so they say how many standard deviations from the mean would that data point 59 be? So let's find out. 59 minus 130.
The answer is negative 71.
Negative 71 divided by 24. Negative 71 divided by 24.
It's approximately negative 2.9583.
All right, so about negative 2.96. And because it's negative, that means it would be 2.96 below the mean rather than above. If it were above, z-score would be positive. That's all there is to it. Calculate the z-score and find your answer. Here's number 19. Is this another one? This is another one. All right. So again, 224 minus 145, all divided by standard deviation. Let's find that out. 224 minus 145.
That would be 79.
That would be 79. 79 divided by 30.
It's approximately 2.6333.
All right, 2.63. Since it's positive, we're going above the mean. That's all there is to it. Let's keep it going. All right. Number 19. Here's number 20. Sorry, I kind of blocked out the number here, but it's 422D. 422D. Graph below represents continuous probability distributions of two normally distributed data sets. So we have A and B both centered at the same spot with that dashed line. And the green data set A is a little more narrow, it's much more narrow than data set B. So with regards to the median, mean, and standard deviation here. So I would say for any normal distribution, any like bell-shaped curve like these, the mean should equal the median. It's always smack dab in the middle, right? For normal curves. Now, standard deviation is describing the spread, describing how either spread out they are or how narrow they are. So a curve or a data set with a greater standard deviation would look a little more like orange, data set B. A greater standard deviation means it's more spread out. And a smaller standard deviation means it's a little more narrow, like data set A. So I'll just say, or how are they wording it? Lower, greater, I don't know. I'll just say smaller standard deviation, and orange has the greater standard deviation. But both of them have the same mean and median because they lie right in the middle. Or like they lie in the same spot. Their middles are in the same spot. Standard deviation of A is greater than the standard deviation of B. No, that's backwards. Standard deviation of B, the orange curve, is greater than that of A. So first one's wrong. The mean of B is equal to the median of A. True, because all the means and medians are equal since they're all in that same middle spot. So only 2 is correct. That was a little glimpse into those. I think we have one more that's similar, but more for a right skewed curve. For a skewed curve, if I remember right, I think the median will follow the bump. So the median follows where the majority of the data is, but the mean still stays a little closer to the middle. Okay? So if you have a right skewed curve, a right skew is like it's describing where the tail is going. So this has a right tail, so it's right skewed. In this case, they say the mean is greater than the median. To be greater just means it's like further to the right. So the mean is in fact greater than the median since it's further to the right. Then they say the data is concentrated to the right. Not quite. The curve is a right skewed curve, but the data where it's concentrated is represented by this big bump that is to the left. That big bump is like if you imagined all the data kind of like stacked up. Excuse me, goodness, dusty. Imagine like a bar graph of a bunch of little bars stacked up in here. It's a little rough, but hopefully you get the idea. Basically, like the majority of the data is stacked up to the left. That's kind of how you want to think about these curves visually. Okay, so this is wrong. Number 2. Come on. There we go. So only 1 is correct. All right, that was 21. I don't know how many more I have here. 22. I think I have at least like a bajillion. I only have a few, I think. That might be the last one. Yeah, so I got like 5, 6 left. Excuse me. That's number 22. So, similar idea, just kind of in a different representation. Really more so using the bar graph kind of idea that I was just describing. So a more narrow data set like population 1 has a smaller standard deviation. So small SD, big standard deviation SD. And again, the mean follows like the middle of the data. So maybe like 7-ish for the mean for population 1, and then a little bit less, maybe like 4 or 5 for the mean over here. Man, I cannot write. Here we go. There we go. Mean. All right. So both the mean for the second are greater. What did I say? Mean and standard deviation for the first are greater than the second. Nope. Mean of the population of the first population is greater than the second. That checks out. And the standard deviation of the second is greater than the first. I think that checks out. And then everything else just must be wrong. So that checks out. Again, the mean of the first was like 7. Mean of the second was like 4. Standard deviation of the second was much greater because it was more spread out. Okay? Got the sniffles. Goodness gracious. All right. below is a distribution with a mean of -3 and standard deviation of 4. Which of the following areas under a normal curve corresponds to this information? So the mean, again, always has to be in the center. So we just want to see the mean of -3 in the center, like this one is. I can't remember how they like translate this one. I think it's more of they want you to like convert it to normalize standard like normal curve with 0 in the middle and stuff. I think that's it. Yeah, so I think for this one you just want to see zeros and 1, 2s, and 3s on the x-axis. So like you don't want to see this, and you don't want to see this 0, 5s, and 10s. You want to see more of a standard normal curve, which would have 0 in the middle and -3 to 3 for the standard deviations. So it's like translating something that would have had -3 in the center, and then you're going out 4, 4, and 4 both ways, something like that. But they're translating it so it's into a standardized normal curve, something like that. I think the trick is just find the 0, the 1, 2, 3, and then find the y values that have decimals instead of whole numbers. So we don't want these whole numbers that B has. We want to choose A because it has the decimals, something like that. Keep it simple. That's pretty much it. Goodness great, I need to blow my nose, but I'm so close to being done. Sorry. I'm just going to be sniffling here. It is known that flipping a large number behaves like a normal distribution. The mean value is n over 2 with a standard deviation of square root of n over 2. If the number of coins flipped is 17,000, what's the probability by percentage that you flip between 8416 and 8525 heads? Ooh, good problem. So we need to find 2 z-scores first. Then we need to find 2. Actually, yeah, that'll pretty much be it. We find the z-scores, and then we find like the in-between probabilities, the in-between percentage between those z-scores. Kind of like we did in one of those other problems that was like probability of 0 less than or equal to z less than or equal to 3. It's that same process. So z-score is basically x minus the mean over standard deviation, right? So we're gonna just use Excel for calculating the z-scores here. Let's see if I can do that in an organized fashion here. Let's try like x and the mean and standard deviation, and we'll put our 2 x values here and here. I'll do 8525 first, and then 8416 second, and then we'll do the mean for, I guess the mean's the same for both. So, oh goodness, I'll just type it in anyway. So 17,000 over 2, and put equals, and then 17,000 over 2 for this one. Standard deviation will be the same. It'll be square root of 17,000 divided by 2. So this is our standard deviation. Let's go z-scores. So again, for z-scores, we take the x minus the mean. X minus the mean. Close that, divide it by that. And we should be able to just drag this down. That's fun. So it calculates the z-score for us. Not too shabby. And then we're going to find the whole probability that the z-score is between about 0.38. Oh, I did that backwards. Sorry. The z-score is between -1.29 and 0.38. So z less than or equal to. Okay. Oh, let me write that right here. All right, let me show you what I've written. Probability that the z-score is between these two. So kind of using the thing we did earlier as a guide, we will do equals norm S dist of the first z-score, so 0.38, comma 1, minus norm S dist of the second z-score. So we're finding the differences in the I guess percentages of it's like the percentage, finding the differences in the percentage to the left of each of these z-scores. Alright, so again, just do norm S dist with the first z-score minus the one with the second z-score. Hit enter, we get about 0.55 or about 55%. So we get option D, and that's it. So find the z-scores for each one, and then find the probability between them. Again, this is a specific example. This is probably one of the harder examples. Sometimes they might just say, what's the probability that you flip less than 8416 heads? If it's just less than some value, you would just do norm S dist for that z-score. So find the z-score and just do norm S dist. If it's what's the probability that you flip greater than 8416, then it would be similar to something we saw earlier where you would find norm S dist for that z-score corresponding to that x value, and then you would do like 1 minus norm S dist. If it asks for when is it greater, what's the probability that it's greater than that value. I hope that makes sense. It might make sense to some, might be rambling for others of you. I'm very sorry if it is. Definitely consider watching the videos that I've posted on these ones. If it's not making sense, I probably have a little more logical explanation. All right, a little more cohesive explanation. Let's check this one out. I think we just have 2 more here. All right. This one's fun. It's kind of an extension of the last few. So they give us a mean, standard deviation. They say sample size is this. How many specimens have a height less than 57? So same idea. We want to find a z-score. A little bit more direct calculation for this one. They give us the x, the data value. They give us the mean, and they give us the standard deviation. So we just plug them in accordingly. What would that be? 21. Negative 21. Yeah. Sorry, my dog's like whimpering in a dream right now, I think. A nightmare. So we get negative 2.1 for the z-score. And then we're going to find the population. Or sorry, I always say population and not percentage. The percentage that is less than negative 2.1. So we'll just get rid of all this. So we just do norm S dist for negative 2.1. Oh, comma. Oh, God. All right. So you have to do the z-score, and then don't forget the comma 1. You always do comma 1. And then, so this is 0.0178. 0.01786, and then since this is the percentage of specimen that have height less than 57, and we know that the sample size is 5,000, what we do now is actually multiply this by 5,000 to give us the number of those 5,000 that have a height less than 57. So we'll just take this times 5,000. And we get about 89 specimen. Okay. Hope that makes sense. It's not too bad for that one. Again, apply all the same rules. If they said like how many specimen have a height between 57 and, I don't know, 64, you'd find z-scores for both 57 and 64, then do norm S dist for 64 minus norm S dist for 57, find the in-between percentage, and then multiply that by 5,000. Had they said how many specimens have a height greater than 57, you would have done 1 minus norm S dist of that z-score of negative 2.1, and then multiply that percentage by 5,000. That was number 25. 26 questions we did today in about an hour. Pretty good. And this one's very quick. They say we're given a p-value of 0.09 or 0.09 p-value is obtained. For which of the following significance levels or decision-making constant alpha are the test results statistically significant? So p needs to be less than alpha to be statistically significant. So 0.09 is not less than 0.05. It's not less than 0.01, but it is less than 0.1. So 0.1 only is the only alpha for which 0.09 is significant. That's pretty much it. So I'm going to throw a bunch of questions for quiz 10. Hope this gave you a brief overview of everything. It's really hopefully not too hard. There's just a lot of little things, and if you're not familiar with stat stuff, it might be a lot at once. I'm very sorry if it is, but hopefully everything's like a pretty quick learn. I think the hardest stuff might be this, maybe some of the stats. I'm not going to say, I don't know, but hopefully everything's relatively quick to learn as opposed to everything else you've dealt with this year, this semester. So I'm going to scroll through the problems. And again, this might be the last live session exclusive to you all here. So keep that in mind. But also keep in mind when you're studying for the final, you might want to watch some of these quiz reviews. So I'll leave it at that. All right, I'm going to scroll through these. And I kind of want to sit in silence, but also I don't know. I'm just going to start scrolling. Here we go. A lot of people ask me, Carter, how am I going to study for the final? And I tell them, you should look over your past exams. Go into the quiz and test system, click on graded work, and look at your past exams that you've taken. You've taken 4 exams. And I guess also look at quiz 10, since quiz 10 is not on any of the exams except for the final. And if you can go through all those past exams and feel pretty confident on the majority of everything, I would say like, not just majority, maybe like, like 80, 90% of the questions on there you can solve with no issue, like you understand the concepts and everything, then you will be more than prepared for the final. I would just study those questions from the past exams. You should be able to like mark questions from the actual exams that you've taken, and then go into the practice system and view those marked problems and practice those. Try a bunch of them, however many you need, and give them a shot. There is a lot of information. I know there's a lot of stuff that you've learned this semester, but breaking it up by exam, especially like the actual exams you've taken, is probably a really good approach. It's hopefully a really good approach. People have been successful with that in the past, but again, it still takes time. I just think it's a good way to kind of organize it, because I understand that it's a truckload of information. So just do the best you can. If you have questions, I'm always available. Not always, but I'm always open to answering questions. I'm always happy to help. So thanks so much for being a weekly study session member this semester. It really means a lot. Your support is not slept on. All right. Thank you so much. If you have questions, let me know. All right. Bye.